Hello, Math 151. And today we're going to talk about sequences and summations. This is section 11.1 in your book. And to start off, I just want to give you a list of numbers. So imagine that we just had a list of numbers, like so. And of course, we can make any listing of numbers that we want. We actually have a set here. And what's happened over the years with mathematics is people have wanted to figure out if there's some pattern to this set of numbers that we could express. And this is what we end up calling a sequence. A sequence is very much like a function, except it only accepts integers. And so I'll explain what this means. So here is a sequence, a sub n. Now, n is just like our function notation. That would be our input. So n in the sequence, this subscript here, acts just like the input of a function x. The main difference, though, with sequences is n has to be an integer. So unlike function notation where x can be any number that's in the domain, for sequences, n must be an integer. Now, it's common, I would say, in the more hardcore math world to start n with 0. However, your book starts n with 1. There's nothing wrong with that. Just a slight difference. Some people like to start n with 0, some like to start with n with 1. Our book does start n with 1, though. So our sequence, this a sub n, we always put in n in here that starts with 1, then 2, then 3, then 4, and how many ever times we need to do that. Unlike a function where x can be any number here, a sequence only allows these integers. And so what can we do with this then? Well, notice then, with our sequence, our a sub n, is if we write a sub 1, then that means using our equation right here, this a sub n equals n. So if we're saying n equals 1, then a sub 1 equals 1. And let's say I wanted to do that again, but now for 2. Well, if n equals 2, if we look at our formula here, a sub 2, then a sub 2 equals 2. And we could keep doing this forever, or stop whenever we want. I'll just do another one with 3 here. And notice this sequence of a sub n equals n. This sequence will list out, then, this set of numbers I have, 1, 2, 3, 4, 5. The sequence will list this set of numbers out. And that's what a sequence does. A sequence is very much like a function. It simply lists out a set of numbers. And again, the big difference with a sequence is it will only accept integers. And for our book, those integers start at 1. So you do 1, 2, 3, 4, 5, 6, and so forth. So let's check out another example. Let's say we have this sequence here, that a sub n equals 3n plus 2. And a common thing for your book to do is, let me see, it says write the first 4 terms here. So we want the first 4 numbers that this sequence gives. And so we'll simply start with n equals 1. Remember, you start with n equals 1. And then we'll put n equals 1 into the sequence to see what number we get out. So if n equals 1, we have 3 plus 2, which equals 5. And that is our first number then in the sequence. Now the book says to list out the first 4, so we'll get an a sub 2 then. So if we plug 2 into the sequence, 3 times 2 is 6, plus 2 would be 8. And then we'll write out the third number in this sequence. That means n equals 3. If n equals 3, then we have 9 plus 2 to get us an 11. And then finally, since they're telling us to only do 4, because we could go on forever with this, but it says only do 4, so we'll plug in a 4 here. 4 times 3 is 12, plus 2 to get us 14. And there we've done it. We've listed the first 4 numbers of this sequence. So let's check out another example. So here we have another sequence. And now we have something here that's pretty common with what are called alternating sequences, and you'll see why in a moment, is in this sequence, notice we have minus 1 to the n. And so what this does is it actually switches the numbers from positive to negative, and alternates, so commonly called an alternating sequence because the sign alternates between plus and minus. But the book wants us to list the first 4 numbers of this sequence. So let's do that. N starts at 1, and so we'll plug 1 into our sequence. So minus 1 to the first power is minus 1, and then 1 plus 3 is 4. So our first number in our sequence, minus 4. And now we'll go on to n equals 2, the second number in our sequence. Now if n equals 2, minus 1 squared is positive 1, so now we have a positive number. And then 2 plus 3 is 5. And so let's list out the third number. So now n equals 3. So minus 1 cubed is now a minus again. And then 3 plus 3 is 6. And again, why are we stopping with 4? Because that's what the book is telling us. The book is saying just list out the first 4. So n equals 4. Minus 1 to the fourth is a positive 1. And then 4 plus 3 is 7. And there we go. We have listed out the first 4 numbers of this sequence. And again, this is called an alternating sequence because it goes from minus plus to minus plus, and that alternating sign continues forever. So let's check out another example. Here's another sequence from the book. And again, they want us to list out the first 4 numbers of this sequence. And so we start with n equals 1. And so with n equals 1, we'll just plug that into the sequence. So we would have 3 over 6, which does simplify to a half. And there's our first number in the sequence. So we'll look at n equals 2. So if n equals 2, we have a 6 in the numerator and a 7 in the denominator. And there's our second number in the sequence. They want us to do 4, so we'll go to n equals 3. Now if n equals 3, looking at our sequence, means we have a 9 in the numerator and then an 8 in the denominator. And then finally, for our fourth number in this sequence, when n equals 4, the numerator would be 12 and the denominator would be 9. And this does simplify to 4/3. And there is the first 4 numbers of our sequence. So all numbers don't have a relationship like this. In other words, you can easily list out some set of numbers that's not going to have a relationship that lists those out. And this is similar to functions that not everything can be expressed as a function. For instance, a circle, something as simple as a circle, is not a function. It fails the vertical line test. So not everything can be written as a function, and with sequences, not all numbers can be expressed as a sequence. So there is another way that we can express numbers using recursive relations. And a recursive relation means that your outputs are all based upon the previous output. And so what do I mean by that? Well, with a recursive relation, we always have to have some defined starting point. In other words, I have to tell you where we're starting. I have to tell you what the first number is. Now, once the first number is given, then we have to define some relationship to the second number. So I'm just going to make up some relationship here. So let's say the next output is always going to be 2 times the previous output. And so that's what I'm defining then with the second equation. This is a recursive relation then. It tells us how the next output, a sub n, is always going to be 2 times the previous output. So what would these first 4 numbers look like then? Well, the first number is given, so I'll just write that down again. And now we want to know what the second number is in this relationship. So we'll simply do that. If we plug in n equals 2, then n equals 2 means 2 times, now we're plugging in n, so we have 2 minus 1 means a sub 1. So a sub 2 is 2 times a sub 1, and a sub 1 is 1. So 2 times 1 gets us 2, and so 2 would be our second number in this sequence. What about the third? Well, the sequence tells us that it's always twice times the previous output. So if we have n equals 3, we'll use our recursive relationship here. So when n equals 3, this equals 2 times a. Now 3 minus 1 means a sub 2. And we just figured out what a sub 2 is. A sub 2 is 2. So that's a 2, and then 2 times 2 will get us a 4. And again, we're only listing out 4 numbers because that's what the book is telling us to do. So we'll go to our last one, our n equals 4. So we'll look at our recursive relation. When n equals 4, we're going to have 2 times a sub 3. And we know what a sub 3 is. It's 4. So we have 2 times 4 to get us 8. And there are the 4 numbers of this recursive sequence. So again, we started off with a sequence that acts very much like a function, meaning one input gives us one output, and we can figure out any number we want. We can just plug in the n value, and we can figure out whatever position. So if we want to know what the 100th number is, well, we can just plug in n equals 100, and we can get that 100th number. With recursive relations, though, we always have to list out every number until we get to the number we want. In other words, with the recursive relation, if I want to know what a sub 100 is, if I want to know what a sub 100 is, well, if we look at our recursive relationship, a sub 100 is 2 times a sub 99. So the only way I can figure out a sub 100 is if I also knew a sub 99. So recursive relationship, we'd have to list all those numbers to eventually get to the position we want. So let's check out another example. Here's another recursive relation. And again, with recursive relations, we always have to be given the starting number. Where does it start? Because recursive relations are always built upon what the previous numbers were. Now, for our book, they only relate to the one number. Recursive relationships could actually relate to many previous numbers. But for all our book examples, we're only going to one previous number. So, for example, I might have to list out an A1 and an A2, and we could base some recursive relationship off those first two. The most famous sequence of numbers in math, the Fibonacci sequence, it actually does use two previous outputs to get the next output. But for our stuff, we only have one output that everything's based upon. In this case, this A sub 1. And we want to list out the first four numbers in this sequence. So A sub 1 is given, so we'll go to A sub 2. So now n equals 2. So we'll go to our recursive relationship formula here, and it says when n equals 2, we're going to have 3 times A sub 1 minus 1. And now we know what A sub 1 is, because that's given to us. We know A sub 1 is 5. So then we can see this is 15 minus 1 to get us 14. And then we'll check out what the third number is when n equals 3. So we'll go to our recursive relationship right here. When n equals 3, we're going to have 3 times A. So 3 minus 1 gets us a 2, and then minus 1. And now we just figured out what A sub 2 is. We just figured out that's 14. And so we're going to have 3 times 14 here to get us, say, 42, and then minus 1 to get us, say, 41. And then finally, because they want us to list out 4 numbers, we then go to n equals 4. So we'll look at our recursive relationship. When n equals 4, we're going to have 3 times A sub n is 4, so 4 minus 1 is 3, so A sub 3 minus 1. And we just figured out what A sub 3 is. We just figured out that's 41. So now we're going to have 123 minus 1 to get us then 122. And then those are the first 4 numbers of this recursive relationship. So let me just quickly summarize what we've done here then. So we have a sequence given by this example here. And then the next thing we had was a recursive sequence. And a recursive sequence always has to have some starting number, so some first number we're given. And I'll just make that different from the last one. I'll say that's 2. And then recursive sequence then always has to have some relationship between the previous output and the next output. And so I'll just make something up here again. I'll say that that's n minus 1 plus 1. So this is what we've done so far. We've had a sequence which acts much like a function, except you put integers into the sequence, starting with n equals 1. And then we have our recursive sequence, which is a sequence of numbers that's based upon the previous numbers outputted. And again, a recursive sequence always has to have some starting number and then some relationship on how the next number relates to the previous number. And just a quick comment here, if you're asking yourself, okay, this just seems all like a bunch of math jargon gibberish. Why is this useful? And the best example I can give you probably is that not everything, certainly not everything in life, can be described by continuous numbers. So, for instance, even if I count the number of students in our class, that's an integer number. And so if I want to do an analysis on our class, then I would have to use something more along the line of a sequence, because a sequence uses integer inputs. And if I'm going to talk about the number of students in our class, well, that is an integer number of people. You can't have 1.3 people. So when you're analyzing things that are discrete in nature, that's when sequences will come into play. So that's all the book has to say about recursive sequences. They actually end with that, and then they go back to regular sequences again. So let's take another set of numbers again. Let's list out some positive integers there. So here's a sequence of numbers. And another thing that's common to do when you have a sequence of numbers like this is to add them all together. So if we added all these numbers together, we'd have 2 and 4 is 6, 6 and 6 is 12, and then 12 plus 8 is 20. So if we added all of those numbers together, we'd get 20. And there is some mathematical symbols to express summing this all together. So what did we do when we summed this all together? We did 2 plus 4 plus 6 plus 8. But let's put this into our sequence notation. So notice that 2 in our sequence we would call a sub 1. The next number, this 4, in our sequence, we call that a sub 2, and so forth. The next one would be a sub 3, and then a sub 4. And so that's what we're doing with these numbers here. When we added them together, 2, 4, 6, and 8, another way we can express that is that we're adding together these sequences of numbers, A1, A2, A3, and A4. And there's some new notation that is a command of sorts. It's an instruction that's telling you to add these numbers together, and that's the summation symbol. And let me just pull that up on the word editor here. Here is the summation symbol. This is a Greek S. And notice in this first box here I'm highlighting, that's where our sequence goes. And then the bottom of the summation indicates at what integer we're starting our sequence. And the top of the summation indicates at what integer we stop our sequence. So this summation, what does this mean? This summation means adding together then all these sequences, all these numbers. So the next thing in our book is the summation symbol. So let me give an example of this. And let's give a new sequence here. And let's say, I'm just going to make one up. Something not too complicated. Let's say we just have 2 times n. So here's our sequence. Now for the previous problems we just talked about, the book wants you to list out the first 4 numbers of the sequence. And that's what we've done so far. And now the book's going to switch, though, to the summation symbol. And now what they're going to say is sum together all the numbers in this sequence. Now, the book will be kind to us, and they, let me just double check really quick. And they do Well, there are some problems that do go to 6. Ooh, here's one that goes to 9. We'll just do 4 here. So there is one homework problem that has us go all the way up to 9, which means we'd have to add 9 terms together. But we'll just do 4 here for our example. So here now are the two pieces of information we have. So the summation means add together all of these numbers. So I just want to write this out to be as clear as possible on what we're doing here. So we know a sub n, we know this a sub n right here is 2n, because that's what we've defined it as. And so what does this equal then? So the sequence, the summation says start with n equals 1, and so that's what we'll do. N equals 1, and so 2 times 1 is 2, which is the first number in our sequence. Now that we've done n equals 1, we now hit the summation symbol, and the summation symbol says add the next number. Now the next number occurs when n equals 2. So now that n equals 2, we have 2 times 2 is 4. And now the summation symbol says add the next number. Now the next number occurs when n equals 3. So when n equals 3, we have 2 times 3, which is 6. And then the summation symbol says add the next number. And now n equals 4. So now we have 4 times 2 is 8. And now the summation symbol says you've reached n equals 4, and now you're done. And so now we'll add all that together, and then we get our 20. So the summation symbol is a way to compact long expressions. So for instance, if our sequence did go up to 10, so instead of 4, let's say this was a 10, we'd have to list out 10 numbers here and then add them all together. So let's check out an example from the book. Here's a problem from the book. They want us to add together 6 of these numbers from the sequence. Let's check out what that is. We'll write these out one at a time. So we start with I equals 1. And we plug that into the sequence. And so we get 5. And now we keep adding until we get I equals 6. So here's the first number. Now I equals 2. Our second number is 10. Now I equals 3. So our third number is 15. Now I equals 4. So our fourth number is 20. Now I equals 5. So our fifth number is 25. And then I equals 6. Our sixth number is 30. And now that we've reached the top number of the summation, we are now done. And so this summation lists out the first 6 numbers, and then the summation symbol says add all those 6 numbers together. And so what do we got here? We've got 55, 75, 90, 100, 105. And that's our answer. This summation right here equals 105. So let's check out another example from the book. Now this time they do use K. You can actually use any letter you want. I is probably the most common, but you can actually use any letter here. So in this case, the book is using K. And the first thing I think that's good to do here is simply list out what these numbers are. So let's start with K equals 1. When K equals 1, we will have a minus 2 times 3. So K equals 1, and we'll just plug that in. minus 3, I'm sorry, minus 2 times 3 to get us then a minus 6. And that's our first number. So now that we've done k equals 1, we'll go to k equals 2. So we'll plug that in. 2 minus 3 will get us a minus 1. And then 2 over here, 2 plus 2 will get us a 4. And then 4 times minus 1 will get us a minus 4. And now we're at k equals 3, the third number in the sequence. Now when k equals 3, we'll have 3 minus 3, which is 0, and then 0 times 5. So we'll have a 0 there. So 0 is our third number. And then finally, we're at k equals 4, which is where the summation stops. We'll have k equals 4, so we'll have 4 minus 3, which is 1, and then 4 plus 2 to get us a 6. And so there we go. We've listed the first 4 numbers, and now we're going to add them all together to get then minus 4. And that is the answer then to this sequence. I'm sorry, this summation. The summation here is minus 4. Let's check out another one. We're going to sum 4. So this one always messes with people's heads a little bit when they first learn this stuff. Because notice this sum here, there's no I in it. So this means the sequence here, remember this, what I have in light blue here, this is the sequence. This sequence is always 4. So this is equivalent to a constant function, something that's not changing. This sequence always outputs the number 4. So what happens then when we write this sequence out? So this is a book problem. They do start with I equals 3, which you can do. So when I equals 3, what is our sequence outputting? Well, it's outputting 4. And that is I equals 3. And now we go to I equals 4. When I equals 4, what does the sequence output? It still outputs a 4. So now we're at I equals 5. When I equals 5, what does the sequence output? Well, it still outputs the 4. And now we have when I equals 6 and when I equals 7. And then we just add all these together. So we got 1, 2, 3, 4. We got 5 4s to get us a 20. So the constant sequence sometimes messes with people when they're first learning this stuff. And it works just like a constant function. No matter what value you put into that, it's always going to output the same number. And so this notation right here, it means just adding 4 together 5 times. So all this stuff so far has really been about notation and understanding what the sequence notation means, the recursive sequence notation means, and the summation. This really just been all about notation and how to understand what this new notation is, and then just chugging through these problems. In other words, I don't think there's too much mathematical thought here. We're just carrying out these commands that the math is telling us. So the summation really is a command. It's telling you to add all these things together. And we're just following that instruction. The last type of problems in this homework are the ones that do require some thinking, though. And in this case, they're going to give you the sum of the numbers here. So I'm giving you a sum here. And what the book wants to know then is how can we write this then in terms of the summation symbol. So the last set of problems, the book is going to give you a sum of numbers, and then your job is going to be to think about how to write this then into the summation symbol notation. So first off, notice everything is going to be squared here. So all the exponents are 2. And notice the base increases by 1. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So what's happening here then is we have the base, which is what's changing, but the exponent stays the same. So this summation of numbers we're seeing here can be represented by I squared, where I would start at 1, so that would give us our 1 squared, and then the summation ends at 15, which gives us then that 15 squared. And that's our answer for our summation. Now, fortunately, the book just wants this as your final answer, so you don't have to add all those together. You just have to give what the summation symbol is that lists out that expression then. So let's check out another one. So here's another sum of numbers that the book is giving us. And they want us to write this sum using the summation symbol. So let's look at what we have here. So you can see all the bases here are base 2. So that doesn't change. So we know we have a base 2 here because the 2 is not changing. What is changing this time are the exponents. And again, they're going by integers here. So 1, 2, 3, and then 4, 5, 6, 7, 8, 9, 10, 11. So what's changing here this time is the exponent. And then the exponent starts with I equals 1, and then it ends at 11. And so this summation represents then the adding together of all of those numbers. So let's check out another example. Another one from the book. Got some fractions here. And they want us to write this sum of numbers as a summation. Let's check that out. Pull out the summation symbol here. And we do have a fraction here, so we know we're going to have a fraction for our sequence. So let's look at how things are changing. If we look at the numerator, it's going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this numerator is just I. So if we start I equals 1, so if we start at I equals 1, then the numerator is simply I. So when I equals 1, I equals 2, I equals 3, I equals 14. Now what about the denominator? Notice the denominator is always 1 higher than the numerator. So when the numerator is 3, the denominator is 4. When the numerator is 14, the denominator is 15. So the denominator is always 1 higher than the numerator. And so we can write that then as I plus 1. And this summation of numbers is going from I equals 1 to I equals 14. And so we'll stick the 14 on the top of the summation symbol to tell us when to stop summing. And there's our answer. So this summation expresses adding all of these fractions together. Now, in closing here, I do want to point out some common things that happen with sequences and summations. And let me just list out all the odd numbers. So all of the odd numbers. This is a pretty common sequence to listing out odd numbers. And what this sequence is, does depend upon if you start at n equals 0 or n equals 1. I'm going to stick with what the book does and start with n equals 1. And 2n minus 1, this will list out, 2n minus 1, will list out all of the odd numbers. So notice when n equals 1, 2 minus 1 gets us 1. When n equals 2, we have 4 minus 1 is 3. When n equals 3, we have 6 minus 1 is 5, and so forth. So this is a common expression you'll see, 2n minus 1, and this means listing out all the odd numbers. Now, just in case you do go to other sources, because it is also common to start at n equals 0. Our book doesn't do that, but if you do go to other sources, it is common also to start at n equals 0. And in that case, 2n plus 1 lists out all of the odd numbers. So this is a pretty important sequence, 2n minus 1, 2n plus 1, because it lists out odd numbers. And another important sequence that can happen a lot are the even numbers. And so what does that sequence look like? Well, for even numbers, slightly simpler. Now we just have 2n. And this is for when n equals 1. So notice when n equals 1, we get 2, n equals 2, we get 4, when n equals 3, we get 6, and so forth. And so 2n is a very common way to list out all the positive integers. And as a final statement here, if we do start at n equals 0, then the even numbers then would be expressed by 2n plus 2. So I'm just pointing these out, this 2n plus minus 1, because this is commonly seen for odd numbers, and 2n is commonly seen for the even numbers. And that is section 11.1. It's about sequences, recursive sequences, and the summation symbol. And I will see you in the next video.